Okay, so in this video we're going to be looking specifically at similar triangles. So in the last video we looked at similar figures generally, the idea that two figures are similar if they have the same shape, so that's defined by their internal angles would all be equal, and if their side lengths are all in the same proportion, so if one is an enlargement of the other. We want to focus specifically on similar triangles because when we have similar triangles, we actually don't need to know about all three angles and all three side lengths in order to determine whether the triangles are similar. So, as I said, we've already established that two figures are similar if all corresponding angles are equal and if the ratios of all corresponding side lengths are equal. As I said, we don't need to know both of these things, so that's equivalent to 3 bits of information if we're talking about triangles, because there will be 3 angles and 3 side lengths in each triangle. So we don't need to know all 6 bits of information to know that two triangles are similar. Okay, so this is about what is the minimum information we need in order to be 100% certain that two triangles are similar. Okay, and there are 3, in fact there's a 4th one as well that sort of loosely fits into this. I might add that on as well. There are 4 ways of knowing that two triangles are similar. Okay, the first is, and this is the one that comes up most commonly, if we know that two triangles have the same angles, they must be similar triangles. Okay, the angles define the shape, therefore they're both in the same shape, and one must just be a simple enlargement of the other. So if all 3 corresponding angles are equal, then we know that we have similar triangles. And the way we would write that would be to say that triangle ABC, so ABC, is similar to triangle DEF, and remember the order is important. So this statement suggests that triangle A corresponds with triangle D, that is the angle at A is the same as the angle at D. Vertex. Vertex B corresponds to vertex E, that is the angle at B corresponds to the angle at E, and vertex C corresponds to vertex F, that is the angle at E. C is equal to the angle at F. Okay, so, and then following that we give the reason that we know that they are similar, and in this case the reason is A, angle, angle, angle. They have 3 angles the same. Okay, so the second way that we can know that two triangles are similar, so we don't need to know about any side lengths. If we know that the three angles are the same, we know the triangles must be similar, and then therefore we know that the side lengths must also be in the same proportion. We can also determine that two triangles are similar if we only know the 3 side lengths. Okay, so if all 3 pairs of sides are in the same ratio, then we know that the triangles must be similar. Okay, so if 2 divided by 3 is the same as 2.4 divided by 3.6, which is the same as 2.5 divided by 3.75, then we know that the triangles are similar. Okay. Or you could do those ratios the other way around, 3 divided by 2, 3.6 divided by 2.4, 3.75 divided by 2.5. So obviously you want to make sure that your triangles are oriented the same way, so you're dividing the longest side in one triangle by the longest side in the other. So that's what it means by corresponding sides. Okay, and in this case, they do all, if we divide all the corresponding sides, they do all give 1.5, so that's telling us that the scale factor here is 1.5, and also that the two triangles are similar. So here we would say PQR is similar to LMN, again making sure we've got that order correct, and we know that it's similar because of side, side, side. We have 3 sides that are in the same proportion. The third way is if we know 2 sides and 1 angle, but it must be a particular combination of that information. It must be the angle that is included between the 2 sides. So 2 corresponding pairs of sides are in the same ratio and the included angles are equal. Okay, so we know that 4 divided by 2 is the same as 6 divided by 3. Okay, and given that the angle in between them is the same, 70 degrees, we know that these triangles are the same, or not the same, sorry, that they are similar. So ABC, triangle ABC, is similar to triangle XYZ, and that is because of SAS, side, angle, side. The only exception to that rule is RHS, which is another reason for similarity, okay, which is right angle, hypotenuse, side. So this is specific to right-angled triangles. So the only time where I can know 2 side lengths and an angle, but the angle is not the included angle, is if it's a right angle. So if I know the right angle and I know, so let's say that this is 6 and this is 3 and this is 4 and this is 2, and that's a right angle. Okay, so I've got two sides that are in the same proportion. 6 over 3 is the same as 4 over 2, which is 2. The scale factor is 2. And I've got another angle, but it's not the included angle, so it doesn't fit the SAS category. Okay, but it is a right angle. This fits the RHS category. So these are similar. So if this was A, B, C, D, E, F, we would say that triangle ABC is similar to triangle DEF because of RHS. Please note that just because it's a right angled triangle doesn't mean that the reason will be RHS. So if, for example, we had this, let's say that this is 4 and this is 3.5, and let's say that this is 8 and this is 7, and that's a right angle. This is not RHS because you don't have the hypotenuse. This is side angle side. Okay, those lengths are in the same proportion as those. 7 divided by 3.5 is the same as 8 divided by 4, so the scale factor is 2, and the included angle is known, and so we are back here at this one, SAS. Okay, so example 1, in each of the following, give a reason, angle, 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 side, 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 angle, side, or I guess it could be RHS, but I suspect it's not one of the options, that proves that the triangles are similar, and calculate the scale factor. Okay, so the only way we're going to know that these are similar, it's going to have to be SAS, but we need to check that the sides are actually in the same proportion, because if this is 310, the sides aren't in the same proportion and they're not similar triangles at all. Okay, so the only option is going to be SAS, but we need to actually check that it fits SAS. Okay, so we know that 640 divided by 480, so their corresponding lengths. 640 divided by 480 is 4/3, or controlled enter is 1.3 recurring. And if I check the other pair, 320 divided by 240, 320 divided by 240, control enter is also 1.3 recurring. So those sides are in the same ratio, okay? And the angle in between them is the same, and so therefore we know that it's side angle side. So we know that they're not labelled, so we know that these triangles are similar due to side angle side, and the scale factor, which the question also asks for, the scale factor is 1.3 recurring. So that's what we've worked out up here. Or if we went back the other way, it'd be 480 divided by 640, 0.75 going this way. But as I said, we tend to use the growth one, so the one that's bigger than 1. But answering 0.75 wouldn't have been an incorrect statement. Okay, part B. So we've only got side lengths here, so it's going to have to be side, 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 but we do need to check that they are actually similar. Okay, so we're going to make sure that we do our division. So 11.2, which is the longest side in the pink triangle, divide that by the longest side in the blue triangle, which is 5.6. Okay, 11.2 divided by 5.6, well, that's 2. Let's check that the others are all in the same proportion, or else they're not similar triangles. So 9.2 is the second longest side in the pink triangle. The second longest side in the blue triangle is 4.6. So, 9.2 divided by 4.6 is also 2. And finally, we need to also check, we need to make sure all 3 side lengths are in the same proportion. So 8.8 divided by 4.4 is 2 as well. Okay, so all 3 lengths are in the same proportion. So we know that these triangles are similar because of side, side, side. And we've worked out that the scale factor here is 2. Okay, part C. All right, we've got a right-angled triangle. We've actually got information, we've got more information than we need here, because we've also been given the angles, because the different markings indicate that they're equal. So this double marking at this angle and this double marking here is saying that they are equal angles. That's saying that they are equal angles, and we know that they're right angles. So actually we could use angle, angle, angle. We've also got side lengths, so we could do, 10 divided by 5 is 2, and 9 divided by 4.5 is also 2. So we've got 2 pairs of side lengths that are in the same proportion and the angle in between them. Okay, so we know that these triangles are similar. We've actually got more than enough information than we need here. Triangles are similar, and either be angle, 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 or it could be side, angle, side, or it could actually be right angle, hypotenuse, side. So we've got more than enough information. Okay, so any of those three reasons are valid here. Side, side, side isn't, because we don't know about the third pair of sides. And we want the scale factor, which again we've worked out through checking the similarity is 2. Alright, and then part D here. Now we've got parallel lines, and this is where our parallel line geometry is going to start to come in, that we looked at in an earlier video. So those lines are parallel, okay? So that means that this angle here and this angle here, that and that, they're corresponding. And that's true down here as well. They're also corresponding. And this angle here is a shared angle. Okay, so that's the same in both triangles. So if you were to draw them out as two separate triangles, that angle is exactly the same in both triangles. Those angles are also the same because they're corresponding, and those angles are also the same because they're corresponding. Okay, this length here is 7 and this length here is 10.5, but when you've only got one pair of lengths, you can't possibly know that the ratios are the same. Okay, if you've only got one pair of lengths, okay, you can work out the scale factor between those two side lengths, but without being able to see that it's the same scale factor between another two pair of side lengths, it's useless information. So this is all about the angles. We only know the three angles here. That's what's telling us that the triangles are similar. So triangles are similar. Angle, angle, angle. It's the only possible reason here. Okay. And then now that we know that they're similar on the basis of the angles, we can use the fact that if they're similar, the side lengths must all be in the same proportion, and so therefore we can use the side lengths we've been given to calculate the scale factor. So the scale factor is going to be 10.5 divided by 7, which should be 1.5, I think. Yeah. So the scale factor here is 1.5. The larger triangle is 1.5 times bigger than the smaller triangle. Okay, so the side lengths aren't useful for determining that the triangles are similar. The angles are what tells us that, but then once we know that the triangles are similar, then we know that all the side lengths must be in the same proportion. Okay, example 2 here. In each of the following, give the reason for similarity, then calculate the value of the pronumeral. Okay, so reason for similarity here. We've only got one pair of known side lengths. It's got to be nothing to do with sides. It's all about angles. So we've got a pair of parallel lines here, which means that that angle there is the same as that angle there. Okay. We've got a second pair of parallel lines here, which tells us that that angle there is the same as that angle there. And then we can also use, if we think about that transversal there, and there's various combinations that will tell us that this one up here is the same as this one here. Okay. In fact, when you're talking about similarity, in terms of the angle, angle, angle reason, we actually only need to know two angles. Okay, because if two angles in a triangle are the same, the third one has to be the same, because we know that three angles add up to 180. So in fact, just knowing that two pairs of angles are the same on the basis of them being corresponding angles to do with those parallel lines. So we know that we have similarity. These are similar because of angle, angle, angle. And so now that they are similar, we can use the fact that their side lengths are in the same ratio. So we can either work out the scale factor, okay, and that's going to come from this, okay. So either we work out the scale factor will be 14.4 divided by 12, which I think is going to be 1.2. And then we know that, so we're multiplying by 1.2 this way, so we know that A is going to be 15 times 1.2, which is 18. Okay. Or we use the ratio method, which is what I would do, which is to just divide the corresponding sides. So we know A divided by 15 is going to be the same as 14.4 divided by 12, and then get your CAS to solve that for you, or 14.4 divided by 12, multiplying both sides by 15. So we just do 14.4 divided by 12 and times by 15, which gives us 18. Okay, so either using the scale factor or using that sort of ratio method. I'm just going to shrink that working down because it's, sorry, I might need a new battery in my pen. bit smaller so that we've got a bit more room here. Okay, in part B, so we don't know any angles in the pink triangle, so it's going to be nothing to do with angles, the similarity. So we're going to need to check the ratios of the side lengths. Okay, so the longest side length here is 16, the longest side length here is 8. Okay, so 16 divided by 8 is 2. The second longest side is 14, second longest side is 7. 14 divided by 7 is also 2. Longest side here is 12. Shortest side here is 12. Shortest side here is 6. So 12 divided by 6 is also 2. Okay, so we've got the same scale factor. Okay, so these ones are similar because of side, side, side. Okay. And so now that they're similar, we know that all the side lengths are in the same proportion, which is, a scale factor of 2, and all the angles will be equal. Okay, so therefore we're trying to work out A, which is the only pronumeral here. So A is between the two shortest sides, 12 and 14. And so in our other triangle, we want to look at between the two shortest sides. So this angle up here is actually the one that corresponds to A. So you need to be careful about the diagrams aren't drawn to scale, they're rotated around, so you need to actually think about the information, not what it looks like. So that angle up there is what we're after, and so we're going to need to use the triangle angle sum to calculate that. So we know A will be 180 degrees, take away 71 degrees, and take away 67 degrees. 180, take away 71, and take away 67. So A is 42 degrees. Okay, part C. Again, when you've got, these are quite common examples where the similar triangles are sort of entwined with each other. And the first thing I would suggest you do is draw them out as two separate triangles so you can be clear about what's what. Now, we've got right angles in both triangles, so those angles are the same. These are corresponding angles, so they are the same, and this is a shared angle, so that is the same. So we know that these are similar because they have 3 angles the same. Okay, and then if we draw them out separately, okay, so there's your right angle, there's that one, and there's that one. So if that's the bigger one, it's 12 and the height is 9, and then the smaller one, we've got that, we've got the right angle, we've got that. The base of that is A, and the height of that is 6. Okay. Now again, you could use the 6 and the 9 to work out the scale factor. It's going to be 1.5. Okay, so either you do K equals 9 divided by 6, which is 1.5, and so we're multiplying by 1.5. Okay, and so then we know that A times 1.5 equals 12, or we do it the other way. We're dividing by 1.5 to go this way, so A will equal 12 divided by 1.5, which is 8. Or we use the ratio. Personally I would do it this way. A divided by 12 is the same as 6 divided by 9, and so A is 6 divided by 9 multiplied by 12, and if we do that with our calculator, 6 divided by 9 times 12 is 8. Okay. Alright, and finally here, again, we need to think about, are the triangles similar? So these two angles are going to be the same because they are vertically opposite each other. Thinking about the parallel lines, okay, if we think about that, there we've got a Z angle going that way, okay, so this angle up here is the same as this angle down here, and if we think about this transversal, if we think about this transversal instead, we've got another Z angle going that way, and so this angle here is the same as this angle here. So the parallel lines here and the vertically opposite angles mean that we have two triangles with the same angles. Okay, so they are definitely similar due to angle, angle, angle. Now again, first thing I would do is reorient them so they're going the same way around. Okay. Alright, so let's have them with both with the yellow angle down here, both with the pink angle over here, and both with the black angle up here, just so we're consistent. Okay, so in the larger triangle, the side length between the black and the yellow is 68, and the side length between the black and the pinky purple is A. In the smaller triangle, the side length between the black and the yellow is 17, and the side length between the black and the pinky purple is 18. Okay, so in terms of corresponding sides, they correspond to each other. That's how you're going to be able to calculate your scale factor. K is 68 divided by 17, which is 4. Okay, so the bigger triangle is 4 times larger, times by 4. Okay, and so therefore A will be 18 times 4, which is 72. Or we use our ratio statement, which is what I would tend to do. I would say A divided by 18 is the same as 68 divided by 17, and so therefore A is 68 divided by 17 times 18. So 68 divided by 17 times it by 18 is 72. Okay, exercise 17E, working with similar triangles.